Okay, this is example number 10 of chapter 13 of section 13.6. So we have a particle or a pin of 0.2 kilograms that is constrained to move in a smooth curved slot defined by r 0.6 cosine of 2 theta meters. The slotted arm, this arm OA, has a constant angular velocity of -3 radians per second. And motion is in the vertical plane. So they say that it's a constant angular velocity. So we know that this angular velocity, the acceleration, will be 0. And they are telling us also that the motion is in a vertical plane. So we know that the gravity goes vertical, right? And that is acting upon the pin. And they ask us to find the force that this arm OA does upon the pin when theta is equal to 0. So if we want to find it when theta is equal to 0, we should draw another drawing, right? In the position that we are being asked to calculate our variable. So we have that curved slot. And we have the arm where that pin is moving. That's a slotted arm too. And the pin is moving between these two. So the pin is right here. And that's when theta is equal to 0. So this is my theta. And when theta is equal to 0, I'm in horizontal position. So the first thing that we have to decide when we're doing the solution is what kind of coordinate system are we using. Since we are given the expression of r and we are given an information about theta, I'm going to use cylindrical component. And since we are given that the velocity is -3, so it's moving downwards, then they are telling us that we can write our system. This is r, this is our r, and that will be our theta. So those are unit vectors that describe our coordinate system. Once we have already chosen our coordinate system, we draw our free body diagram of the particle in the position that we are being asked to calculate, that, right? So this will be my r, and that will be my theta, up right here. And then, what forces do we have acting upon our pin P? We have a reaction force, R, that is exerted from that curved slot over our pin. And then we have a normal force that is done by that arm OA over our pin. So we have two reaction forces, and then we have also the weight acting in the vertical direction, negative, and that will be 0.2 times 9.1. And then we have to make that equal to our kinetic forces. So we draw our kinetic diagram. Our kinetic diagram will be, we will have a mass times our acceleration in r, and our mass and acceleration in theta. We remember that r is equals to r2 dots negative r theta dot square, and r theta is equals to r theta 2 dots plus 2 times r dot theta dot. So before we do our equations, we have to find how much is theta dot, how much is theta 2 dots, how much is r, how much is all the components to calculate our acceleration. That theta, we were told that theta is equals 0, right? And we were told that theta dot is equals -3 radians per second. And we were told that it's a constant angular velocity. So we know that theta 2 dots is equals to 0. Now we have to find the r's. We are told that r is equal to 0.6 cosine of 2 theta meters, right? And then r dot will be the derivative of this expression, which is 0.6. The derivative of cosine will be negative sine 2 theta. We have to multiply by the internal derivative, which will be 2 theta dots. And that will be meters over second. Now we can derive this expression to find our 2 dots. And that will be 1.2, right? Which is this 2 multiplied by this 0.6. And then we have the derivative of 2 functions. This is one function, this is the other function. So I will multiply that by the first function, the derivative of sine, which is cosine theta dot, times the internal derivative, times theta dot. Now I will have these first functions multiplied by the derivative of the second. So that will be negative sine 2 theta times theta 2 dots. This is meters over second square. Now, if we plug the value of theta into our expressions of r, we can evaluate them. So if I plug theta dot, and theta 2 dots, we have that for theta equals 0, theta equals negative 3, and theta 2 dots equals 0. We have that r is equals to 0.6. R dot is equals to sine of 0, it will be 0, right? And then R2 dots is equals to, okay, this sine of 0 is 0. Cosine of 0 is 1. And then I get here, these 2 will be 2.4 times theta dot square. So that gives me 21 negative, right? Negative 21.6 meters over second square. Okay, perfect. Now we applied let me apply my equation of motions, and that is, so my add forces in R equals MAR. So what forces do we have in R direction? Only R. So R will be equal to 0.2 times AR. AR is theta 2 dots, which is 21.6 minus 0.6 times theta dot square. Theta dot square is 3, negative 3 square. So from here we can get R right away, right? Yes, so we can get R. That give us the R is equals to 0.2 times this expression right here, give me a negative 5.4 newtons. And if I add forces in theta, that will be m theta, which is equals to. So we go to our free body diagram, and we see that we have n go in the positive direction minus w in the negative direction equals to 0.2, which is my mass, times the acceleration in theta. The acceleration in theta is right here, but we have here that theta 2 dots is equal 0. So this is equal 0. And we have that r dot is 0 because it's multiplied by sine. So r dot is 0. So actually, we notice that here we have 0. So here we have that our normal is equal to our weight, which is 0.2 times 9.81. So our normal force is equals to 1.96 newtons. And that's our result. Actually, well, we were asked to find the force of the arm OA on the pin P. That was the normal end, so it's 1.96 newtons. So important here is to decide which coordinate system you will use. We use cylindrical components, and then find this expression. I do not expect you to learn it by heart. You can have it in your formula sheet, but I do expect you to derive those expressions correctly to be able to calculate those accelerations.